is up, guys? We just went through 4-4, and it was on optimization. In this video, I'm going to go through two examples of optimization type problems, and hopefully it'll help you guys kind of with your homework and just kind of developing like a strategy when coming about these going through like these types of problems. Okay, so first example, I called it example alpha. All right, because I'm not really sure what number example we're on, but so yeah, I'm going Greek. So here we go. This example, it is from the book, and I like it so much because it makes you think a lot. It's a trickier one, definitely, but hopefully you guys will get it by the end of this thing. So let's just jump right into it. So the situation is this: you have like a sine-looking curve. In fact, it is sine, right? And we know sine looks like that, right? Let's just say this is f of x is equal to sine. And let's mark some important points. That's pi and that's 0. And the goal here is to inscribe a rectangle inside of the sine curve. And I know it doesn't look like that realistic of a problem, but let's say the sine curve represented a piece of land that you could build on, and you only have these straight pieces that you can really use to build your whatever you're talking about. I think we built a pen during class, like for a farmer. But in this case, let's say we're building a house or something, and we don't want to cross any zoning laws and things like that. So this is a prime example of when you want to kind of maximize the amount of area that you're allowed to use, right? Something like that. So let's say we want to build a rectangular looking building, and what we want to maximize this rectangle. Aha. So there it is. That's the goal. We want to maximize this rectangle, and we know the shape of the area we can play with. So we need to come up with some formulas that kind of represent this situation, right? So if we're trying to maximize the rectangle, well, that means we need to use the formula for the area of a rectangle, right? And we know that the area of the rectangle is going to be length times width, which you learned oh so long ago. And yeah, so we're gonna use this knowledge along with our function and stuff to kind of construct a function here. All right, so just think about it. If I'm trying to maximize, just making sure I'm recording, if I'm trying to maximize this red rectangle here, I need to know what this piece is and what this piece is with respect to my function, right? More specifically, well, I mean, like, it doesn't really matter which one's which, right? Because I'll just call this L and this one's W, right? So, actually, width is usually like sideways, right? So let me just quickly change that. This one is, let's call this one length and this one W. Like I said, it doesn't really matter. So here we go. We're trying to figure out the length and the width, right? And we're trying to figure it out with respect to the sine graph, right? So well, let's think about it here. I think the length is kind of easy, right? Because if I want to find out like how tall it is here, or how tall it is here, or how tall it is here or here, if you think about it, what we're using are the actual function values. Does that make sense, right? So that means my actual length value is just going to be the height of the function. It's just going to be f of x. So what we're trying to maximize, we want to maximize an area function with respect to x. So what we're going to first do is multiply by f of x, which is just sine of x, right? But now we got to think about, well, what is the width, right? We got the height. How can we figure out the width of this thing? Why don't you take a minute? I'm going to pause my video, and why don't you take a minute and think about it? So hopefully you paused it and you thought about it, right? So what we're going to do here, I'll use a different color to show. What we notice here is there's an amount here. And I'm going to call this amount x, because if you think about it, it's still too thick. If you think about it, right? this represents how much you went from the origin, how much x value you went from the origin, right? And no matter where we go on the sides of the rectangle, it's always going to be equivalent to that amount. It's going to actually show up on both sides of the rectangle, right? So I can construct a rectangle here, I can construct a rectangle here, or whatever, but no matter what, no matter how I construct the rectangle, the space that's left over, because sine is symmetric, is going to be the same on both sides. Does that make sense, right? So this width here, this total width is pi, right, from 0 to pi, but then we're going to actually subtract 2 times x. And this is the tricky part of the question. I know, it's weird. So what does that mean? For our width, it's going to be pi minus 2 times x. Hopefully you guys came to that when you paused the video. I don't know. Maybe you didn't. But anyways, we get pi minus 2 times x. Oh, I don't know why I wrote it like that, but I'll just rewrite it down here. And this is my area function. This is the thing we are going to maximize. Sine of x times pi minus 2x, because that's what gives us our area with a given x, right? So if I gave you this x value, right, it would give you the area there. Or if I gave you this x value, it would give you the area there, and so on and so forth. I should have used a different color, sorry. Right? So this is what we want to maximize. Okay, well, how do we maximize? This is the easy part, right? We just got to derive. We're just going to derive a prime. I'm going to do this in black now. So I'm going to derive, why is this so thick? A prime of x, right? And look at that. I have a product. I'm going to use the product rule. So it goes first times the derivative of the second. Remember, pi is a constant, so it's just -2. And then plus the second times the derivative of the first, which is just cosine. And if you look here, it's kind of a very complex looking thing. I'm going to guess that if this were given as a problem, this is probably going to be a calculator problem. So what we're going to do is you're just going to actually plug a prime into y1 for your calculator. And just see where it crosses 0, right? Because what are we trying to do? We're going to set this derivative equal to 0 and find that x value, right? We're trying to see if that critical point is going to be a maximum, because once again, we're trying to maximize the area, right? So we need to check, does the graph go from positive to negative at the critical point? So at this point, feel free to bust out the calculator, punch out this thing into your calculator, and we're looking on 0 to pi. So if you want to change your window, make sure you change your window to 0 pi. And then when you plug it in, you should see the derivative graph go cross at some really intense decimal looking thing. If you just use the 0 function, you're actually going to find out the critical point is at x equals 0.7104627, something like that. Some crazy decimally number. Right, and what you're gonna see is so if this is like 1, it's gonna the derivative graph actually kind of crosses like that. That's what it should look like in your window. And what this means is the derivative values are going from positive to negative at this critical point, 0.7104, whatever, right? And that's exactly what we want. That means the original function is going from positive to negative, right? The maximizing function, this a of x, right? That's when that graph is going from a maximum to a minimum, right? That's when the area starts to go from a maximum to a... that's when the area goes from an increasing amount to a decreasing amount. So this is the perfect point. So what does this mean? We found the x coordinate for which to maximize our area. So we're not really done yet. We found something that's going to lead us to the answer, right? So if our if our length was, remember, if our length was, where is it? Oh my gosh. Oh, our length was our function, and our width was pi minus 2x. We can just calculate this right now, right? Our length is going to be f of 0.71046 something something blah blah blah, right? And our width is going to be 2, nope, sorry, pi minus 2 times 0.71046 blah 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 blah. And you can get, you can find your max area, right? I forget what the question was asking, honestly. It was saying like, the question could ask for what are the like measurements, or it could ask like what is the max area you can get. But I'm going to give you both, okay? So the measurements of the length is approximately like 0.65 if you plug it into the calculator, and then the width is going to be approximately 1.72, and then the max area is about 1.12. The book does not do 3 decimal points. That's pretty disappointing. All right. So and that's it. That's your final answer, right? Those are the dimensions. That's the max area, and we're done.